when we draw a tangent line where it touches the curve and maybe crosses. Why? Hey guys, if you draw a tangent line here, I guarantee you that it crosses the curve where you drew it at this point of inflection. So, when we take a tangent line, what does it do? The slope of the tangent line is equal to the slope of the curve at the point of tangency. Okay, so the slope, you end up getting this. Now, yes, okay, h implies that you're dealing with two separate points, and therefore this is a secant instead of a tangent, but when h approaches 0, this is a tangent. Of course, this presumes that the limit exists. Why? Oh, hey guys. That would not have a limit. So, the tangent line has this slope and is through the given point of tangency. Okay, now example 1. So find the slope of the curve y equals 1 over x at any point. What is the slope at the point x equals negative 1? Where does the slope equal negative 1 over 4? And what happens to the tangent to the curve at the point a 1 over a as a changes? Why is this here? Well, we said earlier that the formula is this. So, m is equal to limit as h approaches 0 of, well, f of x0 plus h minus f of x0. And this is over, well, x0 plus h minus x0, so h. Okay. So what is f of x here? Well, it is y equals 1 over x, so f of x is equal to 1 over x. In this case, that means equals limit as h approaches 0 of 1 over x0 plus h minus 1 over x0. And this is all over h. Okay, so what happens when we do this subtraction? Well, we can multiply these two denominators together, and we end up with limit as h approaches 0 of x0 times x0 plus h, and on top we end up with, well, x0 minus x0 plus h. And this is over h. So, I think we get the feeling that this, what else could we get rid of? Should we desire it? Hey guys, we don't care what x0 is. So we could just write this as just x. So what happens when we write it as just that and simplify at the same time? Well, we end up with negative h over x times x plus h, and this is all over h. So what happens when we divide negative h over x times x plus h divided by h? Well then, of course, we end up with equals limit as h approaches 0 of negative 1 over x times x plus h. So what happens next? So as h actually approaches 0, what does this come out to? Oh, hey, x times x plus 0 on the bottom. So that's negative 1 over x squared. Hold on a second. Let's think, does this make sense? Well, okay, at x equals 0, there is no slope. Okay, it's undefined. What does 1 over x look like? Well, 1 over x looks like this. Oh, whoops. Well, anyhow, more or less. So, there is no slope where there's an infinite discontinuity. Okay, that's fine. No surprise to any of us, I think. The slope is always negative. So it's always sloping downward. But here, as x gets bigger, the slope gets smaller. Here, as the absolute value of x gets bigger, we will actually go that way. So the slope gets less negative. Our absolute value of slope gets smaller. Okay, so what happens when we consider what happens near 0? Well, we end up getting slopes that are very large negative numbers. And what happens to negative 1 over x squared as we get near 0? Well, we end up getting closer and closer to negative infinity, and eventually at 0, undefined. Okay, so where does the slope equal negative 1/4? For m equals negative 1/4, we end up with negative 1 over x squared equals negative 1/4. And x squared is equal to 4. Looks pretty obvious to me. Why? Oh, hey, same place. Everything else is the same. So, x is, well, here we can't just say plus 2. I mean, usually when we take the square root, we just say the positive. But in this case, guys, so our graph looks something like this. That means that there are pretty clearly 2 points of any given slope, which means that here we need to put plus minus 2 as the square root of 4. Okay, so what happens to the tangent to the curve at the point a, 1 over a, as a changes? Well, we'd say that the further a gets from 0, the smaller the absolute value of the slope. So less negative. And the closer it gets to 0, the more negative. So here, well, we'd probably state that if we decided to write a statement, at x equals negative 2 or 2, the slope is negative 1/4. Okay, so C. As absolute value of A increases, the slope of the tangent becomes less negative. Now this kind of strongly implies the converse, as in as absolute value of a decreases, the slope of the tangent becomes more negative. Wait a second. Less negative at an increasing rate or a decreasing rate? Decreasing rate. Okay. Now, if we were to take the derivative of a function, hooray, we have finally used that term legitimately for the first time. We write it as f prime of x. Now, why is it here f prime of x0? Well, we said that it's the derivative of a function at a point x0. So if it's just the derivative of the function itself, as in we're looking for another function that tells you what the slope of this function is at any given x, then we would be, f prime of x. Now, of course, there are other ways we can write it, which we'll talk about later. But here, we have this thing that we had earlier. This is the exact same as m, so the slope. Now, this, of course, also presumes that this limit actually exists. In past examples, at some point we might have modeled the speed of a free-falling object from rest near the surface of the Earth. This here, 5t squared, that is an approximation. The actual gravitational field of Earth is not, in fact, 10 meters per second squared of acceleration near Earth's surface. It is actually approximately 9.8. Okay, but if we hold this approximation to be true, we used a sequence of average rates over increasingly short intervals to estimate the rock's speed at a given instant. Well, we probably did that in previous examples at some point in, say, homework or class exercises, because this is a very common type of problem. Well, what is the rock's exact speed at time t when we use the derivative formula above? So, this thing. Well, f of t is equal to 5t squared. F prime of t is equal to limit as h approaches 0. Now, different places use different letters here for the tiny little distance between t0 and t0 plus h, or t and t plus h. So we'd have f of t plus h minus f of t, and this is over, well, t plus h minus t, which is h. Okay. So this is equal to limit as h approaches 0 of 5 times t plus h squared minus 5t squared. This is all over h. So this is going to be limit as h approaches 0. If you do a number of these problems with, say, x squared, x cubed, x to the fourth, and so on, you will notice a very interesting pattern surrounding this. T squared, okay, that's fine, plus 2th plus h squared, okay, and then what? Oh, okay, minus 5t squared. Okay, first we cancel this out, so we don't need that anymore. And then what? Oh, over h. Okay. So what we end up with is going to be equals lim of h approaching 0, bracket, 10t t plus 5h. Okay, what happens when h goes to 0? This is just 10t. If we decided to do this with, say, to the third power, we would have 3 as a coefficient in here, and then all the rest, because all the h's go to 0, after we cancel this one out, what happens? We end up with, 3 comes down here, and then we end up with t squared. Hey, what we've done is taken the exponent, removed 1, and then, take the original exponent and multiply it out in front. We'll get to that momentarily, but, well, this sort of thing, this repeated derivation and going like, I think we see a pattern here, was basically what early mathematicians did to come up with calculus, or derivatives at least, because calculus is bigger than just derivatives. Okay, so this is the rock's exact speed at time t. F of t was distance fallen. So f prime of t is going to be, well, the rate of change of distance is speed. The speed of the rock at time t will be, at time t will be, well, this has to be 10t. Okay. And wait a second, guys. Were there units mentioned earlier? Ooh, 5t squared meters during the first t seconds. That implies that what we put down here has to be suitable units. So this is going to be meters per second. Per second. Okay. So, definition, well, here we once again state the definition of the derivative at, well, what's the difference here? This time, instead of stating it at x0, we state it just at x in general, which makes this slightly different from what we had a moment ago. Okay, now, this of course still presumes that the limit actually exists. Otherwise, well, what are we doing, right? Okay, so now suppose we differentiate this. Hey, if we haven't learned stuff like the quotient rule and such, how can we possibly do this? Well, plug and chug with what we had before. So f prime of x is equal to, by the way, this is how people came up with the quotient rule in the first place, more or less. Other than the fact that they had to come up with the product rule first. But we'll get to that somewhat later. Okay, so this is limit as h approaches 0 of f of x plus h minus f of x. And this is all over h. So, f of x plus h gives us, well, first we have to write this. You'd be surprised at how many little mistakes are made by people forgetting to write the lim part because their brains just jump straight to substituting for this. I've seen it happen. It was very sad. And I do not think I need to expound further on that story. Okay, so this is over h, and well, lim h goes to 0, x plus h minus 1 times x minus 1, and this is going to be x plus h times x minus 1 minus x times x plus h minus 1. And this is all over h. Okay. Please note that teachers don't expect you to be able to perfectly gauge how long your fraction lines are supposed to be, and therefore they do not expect you to be as good in handwriting as you should be if you're doing this in a computerized assignment. In other words, please overlook the fact that this is not exactly a Leonardo da Vinci level of artwork and coordination. I won't talk about Picasso because that's a different story completely. Okay, so lim of h approaching 0. Well, do we have to multiply this bottom part out? Let's not do that yet. Let's just do the top. Okay, so we end up with, on the bottom, x plus h minus 1 times x minus 1. And on top, we have x squared minus x plus hx minus h minus x squared. Why is it important to put this bracket out here? It's because it's surprisingly easy, presuming that you actually put the bracket out there, it's surprisingly easy for a lot of people to forget that this is not multiplying in by x. It's multiplying in by negative x. So because a lot of people forget, brackets can be very helpful for them when it comes to multiplying by negative something. Plus hx minus x. Okay, so here, x squared minus x squared, what happens? Cancel, cancel. And x, well, negative x minus negative x, what happens? Cancel, cancel. And plus hx minus plus hx, what happens? Cancel, cancel. And we're left with negative h minus 0. And this is all over h. So what happens there? Well, we can divide. And this becomes 1. So we end up with limit as h approaches 0 of negative 1 over x plus h minus 1 times x minus 1. So when h is 0, what happens? X minus 1 times x minus 1 on the bottom and negative 1 on top. So negative 1 over x minus 1 squared. Okay, so that's it, because we differentiated this. Is it? Well, usually a lot of teachers tend to like it when on the last step they don't have to look all the way up a whole chain of equal signs to find out what you're equaling. Hence why we wrote this. All right, next.